These are the answers to the practice test on atomic structure and nuclear chemistry. So for these first 7 questions, you just simply have to remember the important information about Dalton, Democritus, Lavoisier, Rutherford, and Thomson. Number 1, his cathode ray tube experiments helped him to discover electrons. We are talking about J.J. Thomson. Number 2, it was John Dalton who published an atomic theory in 1803. Number 3 refers to the Greek philosopher Democritus. Number 4, that would be Rutherford's famous gold foil experiment. Number 5, it is also J.J. Thomson who worked out the plum pudding model of the atom. We have Antoine Lavoisier to thank for discovering the law of conservation of mass. And discovering that an atom contains a nucleus came from Rutherford's gold foil experiments. In number 8, we have to decide whether or not the words that go in the blanks are protons, electrons, and neutrons. If an atom of lithium-7 is neutral, then that means it contains the same number of protons and electrons. So lithium-7 would contain 3 protons, 3 electrons, and 4 neutrons. Number 9, if a neutral atom of oxygen gains, well, remember that if it's an anion, it is negative, and cations, as you can see, are positive. So we're looking for an anion, which is negative, so we are gaining electrons. Number 10, we have a boron 10 atom, which contains 5 protons, 5 electrons, and 5 neutrons. But in the nucleus, there would be 5 protons and 5 neutrons. Number 11, a neutral atom of carbon-14 is going to weigh a little bit more than carbon-12 because it has 2 more neutrons in its nucleus. So neutrons contribute to the mass, but do not change the identity of the element. Number 12, as you can see from the table you filled out earlier in your notes on atomic structure, the electrons are assigned a mass number of 0 because they are so much lighter than the other subatomic particles. Protons and neutrons have a mass number of 1. In number 13, we're comparing a neutral atom of cobalt-60 with an ion of cobalt-59 carrying a +2 charge. So cobalt has 27 protons. The ion would have lost electrons and clearly has a different mass, so it has a different number of neutrons, but this would also contain 27 protons because it is still cobalt. In number 14, we're comparing beryllium-9 with boron-10. So beryllium-9 has 4 protons, 4 electrons because it's neutral, and 5 neutrons because 4 plus 5 is 9. Boron-10 has 5 protons, 5 electrons, and 5 neutrons. So when we compare these 2 atoms, we can see that they would contain the same number of neutrons. In number 15, we're comparing a sodium-23 cation that has a +1 charge with a fluorine-19 anion that has a -1 charge. Sodium has atomic number 11. It has a +1 charge, so it has only 10 electrons. And it happens to have 12 neutrons because 11 plus 12 is 23. Fluorine has atomic number 9, so it has gained 1 electron, has 9 protons, 10 electrons, and since 9 plus 10 is 19, it has 10 neutrons. So as you can see, the only thing they have in common is the same number of electrons. Number 16, if you recall from your nuclear chemistry packet, alpha particles consist of 2 protons and 2 neutrons. Also in your nuclear chemistry packet, we learned that beta decay refers to a beta particle, which essentially is an electron. And we learned in that same nuclear chemistry packet that a positron has the same mass as an electron, but has the opposite charge. In number 19, we are given the following information. We are told that if a metal from group 1, that would be column number 1 on the periodic table, forms an ionic compound, the charge is +1. So lithium, sodium, potassium, and rubidium are metals in group 1, and they have charges of +1 when they form compounds. It says that a nonmetal from group 17 is going to have a charge of -1 when it forms compounds. So now we're over on the other side of the periodic table. Fluorine, chlorine, bromine, and iodine all carry charges of -1. If we put the positive and the negative ion together to create a compound, it must be written so that the charge is 0. So we need a 1-to-1 relationship between lithium and fluorine, sodium and chlorine, etc. So based on that 1-to-1 ratio, the formula would be LiF, NaCl, KBr, or RBI for these 4 compounds. So we can eliminate choice B because the formula of the product is incorrect. We learned that the elements in group 17 exist naturally as diatomic molecules. So we can eliminate choice D since iodine is not written as I2 the way it should. We also learned that if you are in group 1, you naturally exist as just an individual atom, not as a diatomic molecule. So we can eliminate choice C because it writes potassium as K2, and that's incorrect. So the correct answer to number 19 is A. In number 20, we are referring to the work of John Dalton, and here is what we know from the atomic theory script about John Dalton's 5 postulates. He said that all matter is composed of tiny particles called atoms, that all atoms of a given element are exactly the same, that atoms of one element have properties that are different from those of any other element. Atoms are neither created nor destroyed in any chemical reaction, and that atoms of one element will combine with atoms of another element to form a compound in small, sort of simple ratios. So for example, H2O. So based on these 5 postulates, he did not say that an atom contains a nucleus. That was discovered later. Number 21 is talking about the properties of a cathode ray. We know that a cathode ray is a beam of negatively charged electrons, and that a cathode ray is attracted toward a positively charged plate. A cathode ray can be deflected with a magnet, and alpha particles, not cathode rays, were fired at a thin piece of gold foil in Rutherford's experiment. So the correct answer is that yes, a cathode ray is composed of tiny particles, which are electrons, and we know that electrons weigh much less than protons. But hopefully you can see why statements A, B, and D are false. Number 22, we're looking for a substance that contains the same number of protons as electrons. Well, if the number of protons is the same as the number of electrons, then the atom is neutral, it is not an ion, and does not have an overall charge, so correct answer is D. In number 23, we're looking for a substance that contains the same number of protons as neutrons. Since you know the mass number is the sum of the protons and neutrons, then we're looking for a mass number that's exactly twice as much as the atomic number. So the atomic number for these elements are 19 for potassium, 6 for carbon, 16 for sulfur, and 32 for germanium. So the only substance whose mass is exactly twice as much as the atomic number is A. In number 24, if the number of electrons are the same as the number of neutrons, we can work this out. So we'll start with beryllium, which has atomic number 4, 4 protons, 3 electrons because it lost 1 for the positive charge, and 5 neutrons because 9 minus 4 is 5. In our next example, we have oxygen, atomic number 8, so 8 protons, 10 electrons because it gained 2 electrons for a minus 2 charge, and 18 minus 8 gives us 10 neutrons. So it looks like B is the answer, but we'll go ahead and confirm C and D are incorrect. Atomic number for silicon is 14. This will give us 14 protons. We have lost 4 electrons, so we have 10 electrons, and 28 minus 14 is 14 neutrons. And then chlorine has an atomic number 17, so it has 17 protons and 17 electrons, and 35 minus 17 is 18 neutrons. So correct number of neutrons and electrons being equal, B is the answer. Now for number 25, we have a mystery element X, and all we know about this element is that it has a mass number of 12, it has a charge of positive 1, and it's found somewhere in period 2 of the periodic table. So period 2 contains elements such as lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So there are the atomic numbers for those 8 elements. Well, it says that in choice A, the atomic number of this substance is 6. That's not necessarily true. It says the substance contains more electrons than neutrons. Well, here's an example. Carbon would have 6 protons. It would only have 5 electrons if it has a positive 1 charge, and it happens to have 6 neutrons. So choice B is not necessarily true. And again, neutrons do not necessarily have to be more than protons by looking at this example. So correct answer number 25 is C. It would have more protons than electrons no matter what it is because it carries a positive 1 charge. Number 26 is just asking us to list the correct number of subatomic particles. We have a neutral atom of potassium 40. So potassium has atomic number 19. If it is neutral, it has 19 protons and 19 electrons, and 40 minus 19 is 21. So correct answer for 26 is D. In number 27, we're going to find that it has 13 protons, so therefore it must be aluminum. It has 13 electrons, so therefore it has no overall charge. And with 14 neutrons, it must have a mass number of 27. So correct answer is C. In number 28, this is aluminum, which has the average atomic mass of 26.98. We are talking about aluminum 28 and sometimes comparing it with aluminum 27 depending on the choice. So letter A says that aluminum 28 has a higher percent abundance in nature. Well, considering that the average mass of aluminum is almost exactly 27, the aluminum 27 isotope would be more abundant. So we can rule out choice A. Now, aluminum 28 would not contain one more proton. It would be a different element if that were true. So the number of protons are the same for both of these. So let's go ahead and compare choices C and D. Beta decay means you're giving off a beta particle which has a mass number of 0 and a charge of -1. The other element or the other isotope that is produced in beta decay is going to have a mass number of 28 and atomic number 14. So silicon 28 is produced. Correct answer is D. We have already seen that when you have a positive charge, you have more protons than electrons. If we're looking for a substance that has a positive 2 charge, we need there to be 2 extra protons compared to the number of electrons. So the only choice that does this is D, because 24 protons and 22 electrons. So D is the correct answer. Now for sulfur to turn into a negative 2 charge, it becomes the sulfide ion. That means it's still considered sulfur. So we cannot change the number of protons, but to get a negative 2 charge, we are gaining 2 electrons. Question 31 is talking about an ion of scandium. Scandium is Sc. It has atomic number 21. And with a +3 charge, this particular ion would have lost 3 electrons. So we're looking for a particular substance that has 18 electrons. Let's go ahead and write the number of protons for each of these 4 choices. Chromium is atomic number 24. Titanium is atomic number 22. Silicon is atomic number 14. And chlorine is atomic number 17. If chromium has a +3 charge, it would have lost 3 electrons. It goes from 24 to 21. Titanium has a -4 charge. That means it gained 4 electrons, giving the total of 26. Silicon has a +4 charge, so now it has 10 electrons. And chlorine has a -1 charge, so that means it gained 1 electron. And since 18 electrons was the number we were looking for, the correct answer is D. In number 32, let's look at strontium on the periodic table. The average atomic mass is close to 88, so therefore 88 should be the isotope that has the highest percent abundance. In number 33, we can do the math by multiplying 35 times the percent abundance of chlorine, and then plus 37 times the percent abundance for that particular isotope. So let's see if we can get 35.5 approximately for our answer. Starting with choice A. 35 times 0.86 plus 37 times 0.14, 35.28. I think we can do better than that. Choice B, we do this math and we get almost exactly 35.5, looking pretty good. Choice C, that is too high. It's around 35.9. So based on this math, the correct answer is B. For number 34, you already know how to do a weighted average. It is not A. We don't do that math and then divide by 2. The problem with B and C is that one of them multiplied 85 times 0.72, which is correct. The other one multiplied 85 by 0.28, so it got the percentages backwards. And clearly D is not the way to do a weighted average. So correct answer is C, based on the weighted average calculation. For number 35, if we take away a neutron, it will still be cesium, but now it will have a mass of 132. So 35 is B. In number 36, we have to do the weighted average calculation, but this time we don't know the percentage for each element, so we're going to go ahead and use X and 1 minus X for our percentages. And we can do that because no matter what X is, the percent abundance of each isotope would add up to equal 100% or 1 if we're using decimals. Let's just go ahead and do the algebra. So 121X plus 123 minus 123X equals the average mass of antimony on the periodic table. So negative 2x equals negative 1.24, x equals 0.62. So the 121 isotope is 62%, and the abundance of the 123 isotope would be 38%. Now we are going to do the weighted average calculation for this particular element, and we can multiply each of those mass numbers by the percent abundance as a decimal. So 54 times 0.058 plus 56 times 0.918 plus 57 times 0.020, and then be careful that you move the decimal back 2 spaces on that last one, 58 times 0.003. If you do this math, you get 55.854. Let's go look on the periodic table and see if we can find an element that has an atomic mass, an average mass that's close to that number. Turns out that iron is the best choice. For number 38, we're going to fill in the missing information. I'm going to start with mass number. So our first one would be a mass number of 231, and then 79, and then 137. For the remaining 3 rows, we add protons and neutrons. 15 plus 17 is 32. 45 plus 58 is 103. And 55 plus 78 is 133. Now, let's go ahead and fill in atomic number. So Pa, which is protactinium, has atomic number 91. Selenium has 34 protons. And barium has 56 protons. Now let's go ahead and fill in the electrons. Since the first example, protactinium has no charge, protons equal electrons. Selenium has gained 2 electrons, so now that's 36. And the barium has lost 2 electrons, so that's 54. To get the neutrons, we're going to subtract mass number minus protons. So 231 minus 91 gives us 140. 79 minus 34 is 45. 137 minus 56 is 81. 157 minus 64 is 93. 89 minus 39 is 50. And 80 minus 35 is 45. So all that remains is the symbol with a respect to a charge. We have to decide if this particular atom has a charge. Our first example is gadolinium, which has atomic number 64. The next one is yttrium, atomic number 39. And the remaining 4 elements, based on the number of protons, would be bromine, phosphorus, rhodium, and cesium. And we're getting that off of the number of protons. The mass number is right there. So 157, 89, 80, 32, 103, and 133. As far as the charge is concerned, the gadolinium does not have a charge because protons and electrons are equal. But everything else, except for the rhodium, actually does have a charge. So yttrium has a +3 charge. Bromine has a -1 charge. Phosphorus has a -3 charge. Rhodium is neutral. And cesium has a +1 charge. So now the table is complete. Okay, now we're going to write balanced nuclear decay equations. Seaborgium is atomic symbol Sg. It has a mass of 266 and atomic number 106. We write an alpha particle on the other side of the equation. And now we're looking for an isotope which has a mass of 262 and atomic number 104. So that particular element would be Rutherfordium, Rf. For our next example, chromium has the atomic symbol Cr. It has a mass of 55 atomic number 24. A beta particle would be 0 over negative 1. So our new isotope is going to be 55 over 25, and that is manganese, Mn. For positron emission, we're going to have 0 over 1, and it's again going to be emitted, so it's given off. For electron capture, that electron is 0 over negative 1, and that's going to be written on the left side of the equation. All right, bromine is Br, atomic number 35. Here is the symbol for a positron, 0 over 1. So our new isotope would be 78 over 34, and that is selenium, Se. For gold, the symbol is Au, atomic number 79. Now we're going to do electron capture, so we have to add an electron. So 0 over negative 1, there's the electron, and that's going to produce an isotope with a mass of 195 and atomic number 78, which is platinum, Pt. To fill in the blanks, we've got to do the math. Let's go ahead and fill in the atomic numbers to make our life easier here. So curium is atomic number 96. Calcium is atomic number 20. So what goes in that first box would be 296 over 116. So that is livermorium, Lv. After giving off an alpha particle, we have 292 over 114. This is fluoravium, Fl. In our next example, the atomic numbers of lead and zinc are 82 and 30. So we're looking for a mass number of 278, atomic number 112. This is copernicium, Cn. And then for berkelium and oxygen, the atomic numbers are 97 and 8. We're looking for a mass number of 267, but there's already 4 for the alpha particle and 3 neutrons. So we don't want our number to be 267. It should be 260 to make the math work out, because we have 3 particles on the right. Now for the bottom number, we already have atomic number 2 for the alpha particle, and since 97 plus 8 is 105, we need our atomic number in the box to be 103, so the math works out. And the symbol for element number 103 is Lr for lawrencium. And now on to the half-life calculations. You know from your nuclear chemistry packet that the half-life equation looks like this. The mass of the isotope that is remaining after the decay has occurred is equal to the mass of the original sample of this radioactive isotope. Then we multiply by 1/2 raised to a certain power. And that particular exponent would be the total time divided by the half-life, so the number of half-life periods. In our first example, we have 38 grams of this particular radioactive isotope now, and we're trying to figure out how many grams of it is going to remain after 115 seconds have passed. So the mass of the isotope remaining, that's what we're trying to find. The original mass of the sample was 38 grams, and the total time was 115 seconds divided by what one half-life is worth, and that's 30 seconds. If we do this math, we get 38 times 1/2 raised to the 3.833 power, and that will give us a final answer of approximately 2.7 grams of this radioactive isotope that will remain at the end. In our next half-life example, same equation, but this time we're trying to figure out how many grams of this isotope was originally present 28 hours ago. We know that right now we have 7.52 grams. We don't know the mass of the original sample, and we know the total time was 28 hours. We divide that by the half-life, which is 15 hours. So if we do the math, 28 divided by 15 is 1.87. Therefore, we're doing 7.52 divided by 0.274, and this gives us approximately 27 grams of the original sample that was present before the decay occurred. In our next half-life example, we're trying to figure out what the total time of decay is going to be. We know that we started with 125 grams and that now we have 22 grams. So I'll just write capital N for the exponent. If we solve for this exponent, we have to take the log of both sides. So after I did 22 divided by 125 and I got 0.176, I take the log of both sides, and then that gives me negative 0.754 on the left equals N times the log of 1/2. Negative 0.754 equals N times negative 0.301, and when I solve for N I get 2.5. Now if that equals the total time elapsed divided by the half-life, which is 5.6 days, the total time is 5.6 times 2.5, which is 14 days. In our next half-life problem, we're trying to figure out what the half-life is. We know that we have 12.5 grams at the end. We started with 42 grams. We know that capital N is this ratio of total time divided by half-life. 12.5 divided by 42 is 0.298. Let's again take the log of both sides. Negative 0.526 equals N times the log of 1/2. So negative 0.526 equals N times negative 0.301. N equals 1.75, which is the total time, 3.2 hours, divided by the half-life, which we don't know. The half-life would be 3.2 divided by 1.75, so the half-life is approximately 1.8 hours. All right, well, those represent the answers and explanations to this particular practice test. I hope that was helpful. Thanks for watching.